Hi everyone, this is just a little sort of tag on really to the end of the work we did last session on the maths behind SHM, and it's to look at how that would be represented graphically. So a little animation just to show an object which is oscillating in SHM, and assuming that it's then on a screen that is moving, the path that would be transcribed on that, showing that it's that nice sort of sine function that we've discussed. So just as a quick recap on the graphs we've already covered from the previous session, we know that displacement in SHM is given by a cos function, where it begins at amplitude, so that's why it's a cos function, and therefore we went on to find that the velocity was therefore given by a minus sine function, and that's going to be an important one just moving forward today, and that the acceleration was a minus cos function. Being directly proportional but in the opposite direction to the displacement. So just make sure that you're happy with those, because they are the graphs. They've not changed from the last session. They're the graphs in terms of time. Okay, and that last point again, it's always worth mentioning that acceleration is like that because it is directly proportional and in the opposite direction to the displacement. I'll keep saying that. Okay, and then the equations that we came up with lead on to two further graphs that you need to be able to recall, really. This is genuine, just a little bit of exam recall, easy 1 mark or potential multiple choice questions to consider. So we had two equations, one for velocity and one for acceleration, in terms of displacement instead of in terms of time. And because we've got equations that are in terms of displacement instead of time, we can also model them graphically in terms of displacement instead of in terms of time. So the top one, a little bit of rearrangement of that, I'm not going to go through the rearrangement, actually leads you to this formula. So v squared over omega squared a squared plus x squared over a squared equals 1. And for those who are a bit more mathematically inclined, or have perhaps just seen this before, you might notice that that is the equation of an ellipse, where omega squared over a squared is actually the maximum speed squared as well, because v is omega a. So that leads us to the equation of an ellipse. So it shouldn't be too much of a surprise to find that the graph of velocity against displacement actually leads us to an ellipse. If we think just practically what's going on, then we are essentially starting at amplitude, start at minus amplitude, okay, and then from there we are accelerating towards equilibrium, okay. So we'll make from minus amplitude, we'll accelerate towards equilibrium, and that will be therefore a positive acceleration, and therefore will give us positive velocity. It reaches equilibrium here at maximum velocity, then from there slows down, oops, sorry, that's terrible, slows down to amplitude on the other side, and then just reverses the cycle back in the opposite direction. And we get that sort of shape there that I've made a bit of a botch going over. So it's an ellipse shape for velocity against displacement. For acceleration against displacement, we know it is directly proportional in the opposite direction. So it shouldn't come as too much of a surprise to see that that graph is a straight line graph. But the key thing with this one is that it is not a relationship that is continuous. It has limits, okay? It doesn't displace beyond amplitude, so minus and plus the amplitude here. Which means that there's also a maximum and minimum acceleration. So throughout the cycle, it's actually going down the line and then back up the line and then down the line and back up the line, rather than actually extending beyond it. So it does have limits, and that is really important to note. And those limits are obviously positive minus the amplitude and plus or minus a omega squared, which is the maximum acceleration. Final little bit to consider is how this relates to energy. So we're going to look at this both in terms of time, because we've not done that yet, and in terms of displacement. So just bear in mind what's actually going on in terms of energy. We've got systems that we've got a continual transfer of energy between potential and kinetic stores. Depending on what the type of system is will depend on what type of potential store we've got, whether that's gravitational, elastic, potentially even a combination of both. but it will be a combination, it will be transfers from the potential to kinetic and back again. The potential energy is at maximum at the amplitudes. That's where you've got zero kinetic energy. And then the kinetic energy is maximum at equilibrium, where the potential energy is at minimum. Been very careful with the words there. I've not put where potential energy is zero. It is at a minimum. Now the graphs will show it as zero, but this is just from assuming that equilibrium, we're not adding any energy in or out. You can consider the potential energy to be zero compared to the rest of the system's conditions, but in reality it will always have some potential energy, so measuring it from that as a reference point, calling it zero at equilibrium, but it might not truly be absolutely zero. In fact, it definitely won't be. And then also remembering, just from simple conservation of energy, the total energy of a closed system, so we've got no transfer of energy to the surroundings, no external forces acting, is constant. So what that looks like in terms of a graph, well, we know the velocity expression already, minus omega a sine omega t. So the kinetic energy is therefore just that multiplied by half m and then squared, so it's half mv squared. So we've squared that velocity term multiplied by half m, which are just constants anyway. What that means is that our energy time graph is a sine squared curve. Okay, it loses the negative because we've squared it, and that makes sense because energy is positive, it's a scalar quantity, and we get a sine squared curve like that. Now, the total energy is constant. So the red line is kinetic energy, but the total energy is constant, so that doesn't change. So if we drew a line for total energy in the system, it would just be a straight line like that, which means that the potential energy is the total energy minus the kinetic energy, and that just gives us the sort of the flip of the kinetic energy curve. So it's a 1 minus sine squared curve, and it's this gold one here, so it's just a mirror image of the original. Again, really important that that you do understand those different graphs as we're going through. Looking at it in terms of displacement, there is a subtle difference here. So what we've done here is we've looked at our velocity expression in terms of displacement again. Okay, whereas previously we'd looked at it in terms of time. So we've gone back to that one. I've squared it already here just to make it a little bit simpler. And what you'll see is that, well, omega squared and a squared, they're both constants, the angular frequency and the amplitude. So if we go for kinetic energy, which is that value v squared multiplied by half times mass, what you'll see is we're actually, it looks a bit complicated, but when you break that down, it's actually a quadratic equation, so it's going to yield a parabola, and because it's minus x squared, it's an inverted parabola. So the energy displacement graph looks like this, where equilibrium is in the middle of this one, and we start at an amplitude with a kinetic energy of 0, and then from there we accelerate, and through equilibrium we're at maximum kinetic energy, and then we go to the opposite side, amplitude, and we're back at 0 again. Now what's key here is that while this is a continuous cycle, it doesn't leave the confines of this graph. It's similar to what we discussed with the previous displacement graphs earlier on, where they are limited. They don't continue beyond this point. They actually just follow the path. If I just sketch over it so you can sort of see what I'm talking about. So they follow this, and then once they're there, they then go back along this same curve and come back down this side, and that's the cycle that repeats. So it doesn't go beyond this. So don't get the displacement graphs confused with the time graphs that are continuous. These are confined, they have limits, which is minus the amplitude and the amplitude. Again, total energy is constant, so it's a straight line across the top, but again it's confined between those two values, minus a and a. It doesn't extend beyond there. And because our total potential energy is just the total energy minus the kinetic energy to preserve conservation of energy, we actually just get a normal parabola for that one, again, that is confined between minus a and a. So really important that you just cement those in your head. Okay, so that's just a little introduction to the graphs. and we'll continue looking at some specific examples of the spring mass system and the pendulum moving forwards.